Okay. So in the multiple choice on the AP test, this type of question is a favorite. They like to put one of these in there every year, sometimes even more than one, where they say that some function y is equal to some other function u times some other function v, or maybe that function y is equal to u divided by v, or there might be any other number of different iterations of this where they give you some function that is somehow related to these other two functions. And then they give you a bunch of values of u and values of u prime and values of v prime, all evaluated at, let's say in this case 2, but sometimes lots of other numbers that they might evaluate it also. They might evaluate it at 2 and 3 and 7 and all kinds of stuff, and give you excess information that you don't need. So what they'll ask you then is to find the derivative of y evaluated at some value. And so first we're going to do this with y is equal to u times v. So if you want to find out what the derivative of u times v is, you have to use which rule?
Product rule.
You got to use the product rule, right? So y prime is equal to u times the derivative of v plus v times the derivative of u. And if we want y prime of 2, then it ought to just be u of 2, which is what?
3.
3 times v prime of 2, which is 2, plus v of 2, which is 1, times u prime of 2, which is negative 4. So what do we get?
2.
2, right? Easy enough. If you've never seen this question before and you sit down to the AP test and look at it, it might look a little confusing because they just give you all this information. But once you realize that, oh, it's just using the product rule, well, that's pretty straightforward then. So what if we were using y is equal to u divided by v? What would y prime be? What's the quotient rule? Should be, what comes first?
It's v times the derivative
of u.
Minus
u times derivative v
over
v squared.
Cool. So if we want y prime of 2 with y equal to u over v, then just plug all those in. V of 2 is 1. U prime of 2 is negative 4. U of 2 is 3. V prime is 2. And then in the denominator, v squared is 1 squared. And what do you end up with this way?
Negative 10.
Perfect. Easy enough. Anybody have any questions or issues with that? All right, cool. So just make sure you're sort of aware that this is something they might ask you about on the AP test. All right. Next little thing we got to throw in here is reasons why a derivative might not exist at a point. And there are 4 reasons why a derivative might not exist at a point. The first is a corner. If the function has a corner, the derivative can't exist. So for example, on the function y equals the absolute value of x, that's what we've got here, the derivative of the absolute value of x does not exist at x equals 0 because it has a sharp corner there, right? It's going from linear to a different linear function. And anytime that happens, the derivative doesn't exist. And the reason being, we can think about this as derivatives are just limits, aren't they? True. And if the slope from the left is not equal to the slope from the right, right? This slope from the left is -1 and this slope from the right is 1. Well, then the limits from the left and the right are not the same. And therefore, the derivative can't exist because the one-sided limits are different for the limit as h approaches 0 of the difference quotient. that make sense?
Yeah.
Cool. All right, next up is a cusp. You may not be familiar with the term cusp in terms of math, but this is a cusp when it sort of narrows in at a curve to a point. So right, this still has a point on it, but we're coming in at a curve to that point rather than linearly from both sides. This is a function like x to the 2/3 power. And the basic idea behind it is the same. These slopes are negative slopes, right? Negative going towards a very large negative, negative infinity. And on the other side, they're going towards a very large positive infinity. So it's going towards negative infinity. And this slope is going towards infinity, right? From the slope from the left and the slope from the right. And therefore, they're not the same on both sides. And it cannot exist. Does that make sense?
Yeah.
All right. And then the third one, a vertical tangent, well, what is a derivative? A derivative is the slope of the tangent line, right? Isn't that what we've been talking about all this time so far? That the derivative is the slope of a tangent line? And what's the slope of something that's vertical?
Infinity
Right, infinity, or
does not exist.
we also just sometimes say that it's undefined, right? That's an undefined slope. And so if the slope is vertical, then that means that that slope is undefined, and the slope of the tangent line, which is the derivative, must also be undefined. Does that make sense?
Yep.
Cool. And lastly, a discontinuity, any discontinuity. And this should make sense because a derivative is a slope of a tangent line to a function. Well, if my function has a discontinuity at the point I'm interested in, and there's no point there, is there a way for me to have a tangent line there?
No.
Nope, can't have a tangent line if there's no point. And so therefore, there's no derivative anytime the function has a discontinuity. Good or no?
Would it only be like discontinuity as like h approaches whatever?
I'm not sure what you mean. Is h approaches? No, it's a discontinuity in the actual function. So as if that limit as x approaches that value doesn't exist, for sure there's not going to be a derivative there. But it's just anytime you have a hole in the graph, there's no derivative at that hole. Anytime you have a tangent, or a vertical asymptote, there's no derivative at the x value of that vertical asymptote. If you have like a square root function, let's say like the square root of x minus 5, if I ask you what's the derivative at -1, well, there's no point at x equals -1, so there can't be a derivative at x equals -1. Does that make sense or no?
Yeah, thank you.
Yep. All right, cool. Any issues or questions on reasons why a derivative might not exist? Those are the only 4 reasons. There are no other reasons why a derivative would not exist. All right. Next small thing we want to talk about is how this relates to the motion of a particle. And we're going to talk about the motion of a particle in a line. That means we're going to be, starting somewhere. Maybe it's at the origin, maybe it's not at the origin, and going to the right, and then maybe going back to the left, and then going back to the right, or the left, or going to the right forever. We're never going to be looking in this class about motion in multiple directions. So we might, our line might be in the y direction. We might have motion going up and down, or right and left. We're never going to have motion that's going like all over the place, or curved around and doing weird stuff in the plane. It's always just going to be motion in a line. So if we talk about motion in a line, and we have a function that we'll call s of t that represents the position of this particle, let's say, that's moving in a line, the derivative of the position function should give us a velocity function. And hopefully that makes sense, because remember that a derivative is an instantaneous rate of change. And so how do you describe the rate of change of the position of something? Well, that's how fast it's changing with respect to time. Well, that's a velocity, isn't it? And anytime we talk about how is velocity changing, well, how do we change velocity? If you're in your car driving, you change your velocity by speeding up, right? By accelerating or by decelerating, right? And so the derivative of velocity, a change in velocity, gives you an acceleration. Good or no? Everybody okay with that or no?
Good.
All right. Then, and we won't need to go much further than this, but the derivative of acceleration gives you a function called the jerk function. Jerk just means, in physics terms, a sudden change in the acceleration. Just out of curiosity, does anybody know what happens after the jerk function? If you were looking for a instantaneous rate of change of the jerk of something, what it's called? Nobody? It's called jounce. You can use that the next time you're playing Scrabble or something. People will not believe you that it's a word. Jounce. But jounce has another name. It is sometimes called snap. Now for the fun part. What's the derivative of snap? For jounce.
Is it crackle?
It is. Yeah, I was going to say, if you had some like cereal for breakfast this morning, it might help you out. What's the derivative of crackle?
Pop.
Pop.
It actually is. What's the derivative of pop?
Rice Krispies.
No, but good guess. I'm pretty sure there was like some awful dance or song or something that told you to do this like 10 years ago or something.
Whip.
No, it has to do with pop. Maybe it wasn't 10 years ago. Maybe it was like 5 years ago. Maybe it was 15 years ago. I don't know.
Block.
Lock, that's right. And what's the derivative of that?
Drop.
I think that's how the song went, right? Was it a song or just a dance? I don't know. Who knows? That's right. Half derivative of snap is crackle. Derivative of crackle is pop. Snap, crackle, pop, lock, drop. What's the derivative of drop? Those of you that are tennis players or like badminton players out there should know this one.
Smash?
Nah, it has to do with drop. But that was good. Yeah, that was good. That was reasonable. What else do you hit? Was that a badminton or a tennis answer?
I'm not sure.
You're not sure. You don't play either one.
I used to play badminton.
Okay. I think this is a badminton thing also. I know it isn't tennis. Like a drop shot, right? The drop shot, make them run up to the net to try and get to the ball or to the birdie. So derivative of drop is shot. Anybody know the derivative of shot? Think track and field.
Shot put, like put.
Put. Yep, that's as far as I know. So position, velocity, acceleration, jerk, jounce, or snap, crackle, pop, lock, drop, shot, put. You don't need to know any of these. But just for fun, we talk about them real quickly, because why not? In a class where we only have 13 weeks to cover 40 weeks worth of material, might as well spend 5 minutes doing these weird things. Those are actually what those are all called, but you don't need to know them. If you know these four, you're good. And jerk function is like really unlikely that you would see that. You're really only going to see these first three: position, velocity, and acceleration. But know that each of these is the derivative of the next one. Now, the other really important thing that I haven't talked about that's on this page here is that speed is the absolute value of velocity. And that's a really, really important distinction, not only for this class, but for those of you that are planning on suffering through another semester of calculus next year, whether you're stuck with me at Scripps or going to college or whatever, that speed is the absolute value of velocity. So velocity has direction. That means if I can say I have a velocity of 5 miles per hour, right? Or I can have a velocity of negative 5 miles an hour. So if I say my velocity is positive, that means I'm either moving to the right if we're talking about in a line, or I'm moving up if we're talking about in a vertical line. And if my velocity is negative, that tells me that I'm moving to the left or I'm moving down. But speed is the absolute value of velocity. Speed has no direction to it. So I could be walking forwards at 5 miles an hour. I could be walking backwards at 5 miles an hour. And the velocity would be different, but the speed would be unchanged. Okay. So speed is the absolute value of velocity. Very important. Everybody good with that?
Yeah.
Okay. And another important piece that is related to this is the position function. The position function tells you the position, right? Which is what it should tell you. It doesn't necessarily tell you how far the particle or whatever the object we're talking about has actually traveled. It only tells you what the position is at whatever t value you're interested in, right? S of 2 doesn't tell me how far the particle moved between t equals 0 and t equals 2. It just tells me where it's at t equals 2. Okay, so this is not a distance traveled. This is just a position. Everybody okay with that?
So the position function doesn't actually represent like how the object is moving in space. It's just like, it's like two-dimensional movement, like as a function of time.
Yeah, so when you get that, that's correct. In fact, it's hardly even a two-dimensional measurement. It's really just a, I mean, this sounds stupid, but it is a positional measurement. It really only says where it is on that number line. So I mean, I guess in a sense, yeah, suppose this is 0. If I say S of 3 equals 5, well, then I'm at that time, I'm at 5. It doesn't tell me anything about what happened between t equals 0 and t equals 3. I could have started here and gone like, ooh, I mean, well, obviously I'd be in a line, but yeah, I could have gone back and forth and back and forth and back and forth and then hit this point at exactly 3, right? Or I could have started right here at this same point and just gone straight to there. It doesn't say which of those I did. It just says that at t equals 3, I'm here. That makes sense?
Yeah.
Okay, cool. All right. Any other questions on that? All right, so let's take a look. I'll give you guys a second here to read this one, and then we will go through and try to work out all the different things that it's asking us for here in this problem. So we've got a particle that's moving along a line, and its position is t squared minus 4t plus 3 for all t values greater than or equal to 0. So I'll let you read through everything that we're supposed to do with this, and then we'll start talking about how we might go about it. Are we ready?
Yeah.
Okay, first off, we want to find the displacement of the particle in the first 2 seconds. So if we want to find the displacement, what does that mean? It means the change in position, right? And it's not a total distance traveled. It's a change in position. All right, hold on one second. All right, sorry about that. So we're looking for a change in position of the particle in the first 2 seconds. So in order to figure out the change in position, we need to know 2 things. We need to know, first off, where did it start? So what's S of 0?
3.
3. And what's S of 2? Where does it end up?
-1.
-1. So we would say the displacement is 4 units. What is it? Meters, right? 4 meters. And we could indicate a direction to that. We could say that it's 4 meters to the left, but the displacement of 4 would be good enough. No calculus there, right? Pretty easy one. All right, what is the average velocity of the particle during the first 4 seconds? So if we're looking for average velocity, right, an average velocity ought to be a change in position divided by a change in time. It's a slope, right? The average velocity is a slope. So what is the change in the position in the first 4 seconds? That ought to be S of 4 minus S of 0. And the change in time would be 4 minus 0. Everybody agree with that?
Yeah.
Okay. Yes. All right, so what's S of 4?
3.
Okay. And what's S of 0? We already got that, was also 3, right? So we end up with an average velocity of 0 meters per second, which tells us that in those first 4 seconds, this particle moved around some, right? Because we know it at least went 4 meters to the left, but it made it back to the exact same position it started at after those first 4 seconds. Good or no?
Good.
All right, cool. Next up then is instantaneous velocity. So now we're getting into the calculus part. An instantaneous velocity of the particle means that it is the velocity at that exact moment in time when t equals 4. Not what was the average up until that point from when it started, but at exactly that moment, how fast was this particle moving? And so this is where we need a velocity function. We need to know what is v of t so that we can evaluate it at exactly t equals 4. So v of t should be the derivative of our position function, s prime of t. And what does that equal?
2t minus 4.
2t minus 4, easy enough, right? So if we want to know the velocity at t equals 4, it's just 2 times 4 minus 4, or 4 meters per second. Good or no?
Yeah.
All right. What about the acceleration of the particle at t equals 4? What is our acceleration function?
The derivative of the velocity.
Just the derivative of the velocity. What's the derivative of v of t?
2.
2. What is the acceleration at t equals 4? What is 2 equal if I evaluate it at t equals 4?
2.
Still 2, right? 2 is just 2 meters per second, or meters per second squared for our velocity. And if I asked you what was the acceleration at t equals 0, what would you say?
2.
Yep, and if I said at t equals 1,000,000, it would still be 2, right? Because no matter what, the acceleration function is 2. This particle has a constant acceleration of 2 meters per second squared. All right, next thing. If we want to know what the motion of the particle looks like and when it changes direction, how are we going to figure out when it changes direction?
The derivative shouldn't exist.
It shouldn't exist when it changes direction, you mean?
Like if it's a corner or something, then it might have changed direction.
Okay, so a place where the derivative doesn't exist would be one case. That's one possibility. And there's another possibility of when it might change direction.
When it's like a horizontal tangent line.
Right, when it's a horizontal tangent line, or when our velocity is 0. Right, because if I'm going to the right and then I want to go to the left, well, I can't just start going to the left. At some point, my motion has to stop, right? And then I got to turn around and go the other direction. And likewise, if I'm going to the left and I want to go to the right, I got to stop and turn around. True? So a place where our particle changes directions could be when the velocity is 0 or when that velocity function is undefined. Now, we're not generally going to have velocity be undefined, but that's a good idea. I'm not sure who said that, but that's a good idea in general. It doesn't work super well with particle motion, but it does work with regular functions, and we're going to be really concerned about when derivatives are undefined by the end of this week. So let's figure out when does our velocity function equal 0 and when is it undefined. First off, the velocity function is 2t minus 4. Is that ever undefined?
No.
No, but it does equal 0, right? When does that equal 0? T equals
2.
2. And so it tells us at least that it changes directions at t equals 2, most likely. Let's look at this on a sine chart. Here's t equals 2. Tell me about the velocity. Here's 0 and here's infinity, right? Because that's our domain for t. T is greater than or equal to 0. Tell me what happens anywhere between 0 and 2 with the velocity. If I plug in any number between 0 and 2, tell me about this velocity.
The velocity is going to be less than or equal. Well, if it's in between, it's going to be less than 0.
Right, it's going to be less than 0, which is telling us that the particle is moving to the left. And what about if t is greater than 2? Like 3 or 1,000,000.
It's going to the right.
Yeah, the velocity is going to be greater than 0, and our particle is going to be moving to the right. And so this ought to be enough to give us a pretty good description of the motion of the particle and tell us that it for sure does change directions at t equals 2. It goes from going to the left to going to the right. So we can say our particle starts at 3, and it moves to the left for the first 2 seconds with an acceleration of 2 meters per second squared. Then it stops moving to the left at t equals 2, continues to have the same acceleration because that doesn't change, and starts moving to the right and continues moving to the right forever. Good or no?
Good.
All right.
We have to write like a whole thing for that, like a whole like sentence explaining it.
If you are asked to like describe out the motion of a particle, yeah. And sometimes they've kind of gone away with it, gone away from it in the last few years, about asking about descriptions of the motion of the particle in the free response on the AP test, but it's still a possibility that they might. And so, yeah, you'd want to write it out, little, 2 or 3 sentences that said that. All right, let's do another one. And in fact, I'll give you guys a minute or two here to read it and do the first part of it for sure. And if you have time, move on to the second part. But we'll definitely do, we'll do both parts together in a minute, but I want you guys to at least give the first part a try on your own. So I'll give you about 2 minutes to do that. And then if you finish the first part, work on the second part also. Ready to go. So if we're looking for the velocity of the stone after 2 seconds, that velocity can be found by taking a derivative of the position function. So what does v of t equal?
-t plus 10.
Yep. I'll just write this 10 minus t, but -t plus 10 is good also. And if we want to evaluate that at t equals 2, velocity equals 8 meters per second. Everybody good with that?
Yeah.
Cool. All right, so then we want to know what's the velocity of this stone after it's risen 25 meters. So we want the velocity at some time, right? Well, we need to figure out what that time is. So how do we figure out what that time is?
Set the position function equal to 25.
Set the position equal to 25. 25 equals 10t minus 1/2 t squared. And it's just now a quadratic to solve, which if we simplify that through here a little bit, and we probably want to multiply everything by 2 and then get it all to one side. So that's going to become t squared minus 20t plus 50 and equals 0, right? Everybody agree with that so far?
Yep.
Cool. And then this doesn't factor nicely. So we'll use the quadratic formula, 20 plus or minus the square root of 400 minus 200 all over 2. And that's 20 plus or minus root 200, which is 10 root 2 over 2, or 10 plus or minus 5 root 2. Everybody agree with all that? There are 2 times at which this stone is at a height of 25 meters. So which one is the one that it is hitting 25 meters on the way up, right after it has risen 25 meters?
The smaller time.
Smaller one, right? Because this is, we're throwing this thing up into the air and it's coming back down. It's parabolic shaped, right? So it's going to hit this height of 25 at 2 different places. On the way up, ought to be 10 minus 5 root 2. So we want to find out what is v of 10 minus 5 root 2, which is 10 minus 5 root 2, or what? 5 root 2 meters per second. If we'd used the other one, 10 plus 5 root 2, we'd have got negative 5 root 2 meters per second. And so that indicates to us that when it's going up, the velocity is positive, and when it comes down, the velocity is negative. Everybody good with that? Hopefully. All right. Once we get into our second time around with this class, so quarter 4, we're going to do a lot more stuff with particle motion. But first we have to learn a bunch of other stuff to add to it. So we're going to kind of stop on particle motion for now and come back to it in a couple months. Any questions on that so far? All right, next thing we're going to do is start learning how to take derivatives of trig functions, which is going to be very important because a lot of the functions we'll deal with will be trig functions. So if we want to find the derivative of f of x equals sine x, and we don't just already automatically know what that derivative is, what can we do to try to find it? How did we develop the power rule and the product rule and the quotient rule? What did we use?
I like limit function, right, for the derivative.
Yeah, we use the limit function, right? We know that the limit as h approaches 0 of f of x plus h minus f of x all over h is the derivative of that function, isn't it?
Yes.
Yeah, so all we have to do is evaluate that limit. Well, how do we evaluate that limit? Plug in h, right? Plug in 0 for h. What do you get when you plug in 0 for h?
Zero over zero.
You get 0 over 0. Bummer. All right, so we got to find a way to simplify it. How can we simplify this down?
Can you use the like limit subtraction rule or something?
So to like separate it into two different ones, you mean?
Yeah.
Yeah, so we could try to do that, but that's going to give us an issue of this is going to give us sine x, which is some number over 0, which is undefined, and then it'll give us another sine x over 0, which is also undefined. So it's just going to give us a couple of undefined things. We're eventually going to have to split it, but we got to do some other work to it first. So you got the right idea. We just got to do some steps beforehand. Anybody see anything in there that has a different way that it could be rewritten?
Kind of, I guess, but somehow could you get that sine of x plus h to become like over x plus h and then simplify that to 0?
There's a possibility of doing that. There is a way to rewrite this. You should at least be moderately familiar with the formula to rewrite this. You don't need to have it memorized, but it's in that trig packet I said to be familiar with. Anybody know what that is? Sine of x plus h, or sine of a plus b, or you probably learned it, if you learned it in like a class last year, sine of alpha plus beta is probably how I used to teach it, at least when I taught honors pre-cal. Sine of a plus b, sine of x plus h is sine x cosine h plus cosine x sine h. That is the sum of angles identity for sine. Sine of a plus b is sine a cosine b plus cosine a sine b. Something you should at least be familiar with. Have you guys seen that before?
Yeah.
Okay, so now we would hopefully notice what about these two terms? What do they both have in common?
Sine x.
They both have a sine x. So I could separate this now into these two limits and factor out the sine x from those first two terms, the first and third terms. Everybody okay with that? So I took the first and the last terms up there, combined them together in one limit, and factored the sine x out of them. And I just put the other term, cosine x sine h over h, in as the second limit. Good or no?
Good.
All right. we should notice something about about either one of these limits, something about each of them, hopefully, that is familiar to us. What's familiar to us in the second limit over here?
Sine h over h.
Yeah, this should be familiar. And what's familiar in the first one?
Cosine h minus 1 over h.
Yeah, this one. So if I were to write this as the limit as h approaches 0 of sine x by itself times the limit as h approaches 0 of cosine h minus 1 over h by itself, I could at least evaluate this one, right? And I could do the same thing over here. And with any luck, we can now evaluate all of these. What's the limit as h approaches 0 of sine x?
0.
Not quite. Remember, this is h is approaching 0. So I replace all the h's with 0, which there aren't any, right?
Oh,
Not
it's
just-
sine x.
Yeah, it's just sine x. Good. And then what about this one? Cosine h minus 1 over h as h approaches 0. That's a known limit that we proved a couple weeks ago. What is that limit?
0.
0?
0. And what is the limit as h approaches 0 of cosine x?
Cosine x.
And what's the limit as h approaches 0 of sine h over h?
1.
1. And what does that give us?
Cosine of x.
Sine of x. So the derivative of sine is cosine. Everybody okay with that? Hopefully.
Yeah.
All right. You will want to memorize and know that the derivative of sine is cosine. You don't need to do this process again, but that's how it's proven. You'll just need to memorize it. Good or no?
Good.
All right. What about the derivative of cosine? What do you think that's going to be?
Sine of x.
Yeah, that seems like a reasonable guess, but unfortunately it's not. We could go through and do this whole same thing, right? The limit as h approaches 0 of cosine of x plus h minus cosine of x all over h. I'm not going to do the whole process. This is me doing the process. Same process. And it ends up being negative sine x. So you'd think if the derivative of sine is cosine, the derivative of cosine should be sine, but it's not. The derivative of cosine is negative sine. Another one you want to memorize. If you're interested in, exactly how to do that, you could go through and try and work it out on your own. Cosine of a plus b, just use the formula for that and simplify. But it'll come out to be negative sine. All right, that's two trig functions that you now know the derivative of, sine and cosine, and you need to memorize them both. How many do we have left to go?
4.
4 more. Unless we're talking inverse trig functions too, then we got another 6 past that. Unless we're talking hyperbolic trig functions also, then we got another 6 of those and 6 of those inverse, but we don't have to do those. So 6 regular trig functions for now. We will deal with the inverse trig functions later this week, but not today. So what about tangent x? Can we do that same process? Tangent x plus h minus tangent x over h. Could, but there should be an easier way. If we want to find the derivative of tangent x.
Wouldn't it be like the quotient rule for sine and cosine?
Perfect. Yep. It could be the quotient rule for sine x over cosine x. So the derivative of sine over cosine, right, this is u over v, ought to be v, times the derivative of u. What's the derivative of sine?
Cosine of x.
Cosine. Minus u times the derivative of v. What's the derivative of cosine?
Negative sine of x.
Negative sine of x. All over our denominator cosine squared of x. So what does that give us? It gives us cosine squared x minus negative sine squared or plus sine squared x over cosine squared x. And some part of that is very easily simplified, right? What do we get?
Numerator is 1.
The numerator is 1, so we got 1 over cosine squared x, which is secant squared x. That's our third trig derivative. Derivative of tangent is secant squared. You're going to want to know that and have that one memorized as well. Good or no?
Yeah.
All right. Derivative of secant x. This should be the derivative of 1 over cosine. And to take the derivative of 1 over a function, we could use the reciprocal rule, couldn't we?
Yeah.
Says negative derivative of the denominator, which is negative sine x, divided by denominator squared, which gives us positive, and it gives us, let's see, 1 over cosine times sine over cosine. And this is normally rewritten as secant x tangent x. So the derivative of secant is secant times tangent. Another one you need to have memorized. So we got 4 of the 6 now. Any questions or issues on that? All right, what about the derivative of cosecant x? That's the derivative of 1 over sine x, isn't it? Gives us negative derivative of sine, which is over sine squared, or negative 1 over sine times cosine over sine, which is negative cosecant x cotangent x. Any questions or issues with that one? There's our 5th one. You need to have that memorized. And last one, 2 good ways to do this one. What's one of the ways? And we'll just do one since we're running a little short on time here.
You could do 1 over tangent.
Sure, that works. The other option would be cosine over sine, right? We can do 1 over tangent x. They come out the same. So this ought to be negative. What's the derivative of tangent? Ought to be secant squared, right? Over tangent squared. So this becomes negative, let's see, 1 over cosine squared. And tangent squared in the denominator is the same as having cotangent squared in the numerator, which would be cosine squared over sine squared. Cancel the cosine squareds and you get negative 1 over sine squared or negative cosecant squared. Good or no?
Wait, can you go to the last slide for a second? Oh, wait, never mind.
Good.
All right, thank you.
Wait, can you go back one slide? Yeah, thank you.
Yep. So here are those 6 derivatives. You need to have all 6 of these memorized. You've got them all sitting there in your notes. So I'll expect that now when I ask you, oh, what's the derivative of cotangent? You just tell me it's negative cosecant squared. because it's either sitting right in front of you or you've spent the minute it takes to memorize it. But you need to have all 6 of those memorized. All right. Finding the derivative of tangent x over x. How will we go about this?
We could use the quotient rule.
Exactly. So f prime of x ought to equal denominator times derivative of the numerator minus numerator times derivative of the denominator all over denominator squared. Any questions or issues with that? Okay. So all we've got now to do is to use the product and the quotient rule to deal with derivatives of trig functions. So again, this one here is a quotient rule problem. Should give us sine x times the derivative of secant x tangent x minus secant x times the derivative of sine x all over sine squared. And we should be able to simplify this down a bit. What's sine times secant?
Tangent?
Tangent, right? That's sine over cosine. And then tangent times another tangent, that would be tangent squared x, and then minus 1 all over sine squared x. Any issues there? Any questions, problems with that? All right, what about secant squared? How are we going to find this one's derivative?
Use like the power rule.
So it seems like the power rule is a good idea, right? Unfortunately, the power rule only works for something like a variable squared. Not yet, at least, for a function, secant x squared. We're going to find a workaround with that tomorrow. But for right now, it would have to be x squared or y squared or u squared or something like that. So is there a way to rewrite this?
Secant x times secant x?
Yeah, we could just do secant x times secant x, right? Wouldn't that give us a product rule derivative? Secant x times the derivative of secant x plus the other secant x times the derivative of the other secant x. And that'd be 2 of these, which is 2 secant squared x tangent x. Good or no?
Good.
All right. Oh, this will be a nice, fun, easy one. Let's find the first 4 derivatives of sine x. First one should be derivative of sine should be
Cosine.
Sine of x.
sine. Second derivative should be
Negative sine.
third derivative should be
Negative cosine.
negative cosine. And the fourth derivative should be
Sine x.
back to sine x. So we know that the sine function is a oscillating function. It's cyclical, right? It repeats itself over and over again. Well, even its derivatives do that, right? Every fourth derivative of sine is itself. Right? The 8th derivative, the 12th derivative, the 100th derivative, the 1000th derivative of sine, since that's a multiple of 4, is just sine of x, which is kind of cool. Good or no?
Good.
All right. Let's find the second derivative of secant x. What's the first derivative?
Secant x tangent x.
Good. And so then we need a second derivative, which means we're going to use the product rule. Right? Secant x times the derivative of tangent, which is secant squared, and then plus tangent times the derivative of secant, which is secant tangent. And what do we get?
Secant cubed plus tangent squared plus secant x.
Secant cubed plus tangent squared x secant x. Yep. I think that's what you said.
Yeah.
Yeah. Any questions with that? Any issues with that? Oh, somebody just left. I've had enough of this already, even though it's just now supposed to be the end of class. What do you guys think? Should we finish these last 3 problems? Should probably let you guys get up. I'm supposed to be in a meeting soon anyway. That ought to be good for today.